are getting ready, let me say, yeah, Zhan, could you make it full screen, please? Yeah, we are ready to go. So our next speaker is Zhan Wang, Chinese Academy of Sciences, and his talk is on interfacial waves under horizontal electric fields, Hamiltonian structure, and bifurcation of solitary waves. Zhan, the floor is yours.
Okay, thanks, Karima. Couple of years. Today, I'm going to talk about nonlinear waves under electric fields in the business called electrohydrodynamic waves. This is the outline of my talk. First, I would like to prove the problem that we discussed is a Hamiltonian system. Then we propose a systematic way in the Hamiltonian framework to derive asymptotic reduced models. Finally, I will show how the electric fields change the qualitative nature of the interfacial solitary waves. Okay, so electrohydrodynamics is an interdisciplinary subject coupling electrostatic fields into fluid flows through the Maxwell stress tensor. Arose in the 1960s when Rayleigh-Taylor and others began their research on interfacial hydrodynamic instability under electric fields. Motivated by the disintegration of water drops in a strong electric field, such as a thunderstorm, Taylor showed that electrified cones could exist in equilibrium with a fixed semi-vertical angle of 49.3 degrees. The electrohydrodynamic instability and the Taylor cone have a wide range of applications in chemistry and industry, including the cooling system, coating process, and the microfluidic device, to name a few. Electrospray ionization resulting from the Taylor cone is an essentially useful technique in converting solution ions into highly charged gas phase ions. It also plays a virtual role in advanced propulsion and power technologies in space science. An applied electric field can exert considerably large forces at electrified interfaces in many situations of practical relevance. And the most important thing is the orientation of the electric field with respect to the undisturbed interface. So in the inviscid limit, the normal form electric field, which is orthogonal to the undisturbed interface, has a destabilizing effect to the system. But the tangential electric field, which is parallel to the undisturbed interface, can provide a dispersion regularization to the system. Well, this can be understood from the linear dispersion relation. If we have a two-layer fluids with a very sharp interface and both layers are semi-infinite, we can quickly write down the dispersion relation. We can include the gravity, surface tension, and electric force. The red terms are responsible for the electric field. For the normal electric field, it is this term is negative. So that means the frequency square could be negative for a strong electric. EB is used to measure the strength of the electric field. So for large E0 for large E0, this term could be very large for a range of K. So that means omega square could be negative, and the system becomes linearly unstable with a very large, sufficient strong electric field. The nonlinear dynamics subject to the destabilizing effect of the normal electric field is also very interesting. This is an example. This is an experiment done by Ozan in 2006, who imposed the normal electric fields to a two-layer system with the background plane Poiseuille flow. The nonlinear dynamics shows a wall-touch singularity and further a drop formation. You will see the drop formation later on, just for several seconds. And the size and the formation rate of the drops are controlled by the applied electric field. Okay. So as opposed to the normal electric field causing instability to the system, the tangential electric field has a stabilizing effect. It can delay the formation of the film rupture and even suppress the Rayleigh-Taylor instability. This is a numerical experiment done by Radu and Dimitri in 2014. The system is in the Rayleigh-Taylor unstable region. Also, the upper layer is heavier than the lower layer. And a horizontal or a tangential electric field is applied, and the electric strength increase from left to right. It is obvious that as the strength of the electric field increases, the electric field can delay the formation of the mushroom structure, which is very common in the Rayleigh-Taylor instability, and even completely suppress the Rayleigh-Taylor instability if the electric field is sufficiently strong on the most right. The Rayleigh-Taylor instability is just suppressed. Okay, so in this talk, we will focus on the tangential electric fields. First of all, let me briefly describe the mathematical idealization of the problem. We use the electrostatic approximation by ignoring the induced magnetic field in the Maxwell equation. Therefore, the Faraday's law implies that the electric field is irrotational. Then you can introduce a voltage potential such that its gradient is the electric field. Then combining the Ohm's law and Gauss' law indicates that the free charge density Q decays exponentially in incompressible fluids. Thus, it is reasonable to assume Q equals 0 in the bulk fluid. And consequently, because Q equals 0, then you can, the voltage potential V satisfies the Laplace equation. Finally, if we take the divergence of the Maxwell stress tensor, it is easy to show that the Maxwell stress tensor has no contribution to the bulk fluid. Well, if you take the divergence of the Maxwell stress tensor, it becomes 0. So, and the coupling of the flow field and the electric field only occurs through the interfacial boundary conditions. Now, we consider two invisible fluids on top of each other in a channel of finite extent in the vertical direction. Two fluids are dielectrics with different electric properties, with different permittivities. And the undisturbed system is under a uniform horizontal electric field. We assume the fluid motion is irrotational, and then we can introduce the velocity potential, which satisfies the Laplace equation. There are 4 boundary conditions at the interface. 2 boundary conditions are for the electric field, the continuity of the electric potential, and the continuity of the electric displacement field. In addition, there are 2 well-known boundary conditions for interface dynamics, the kinematic boundary condition and the dynamic boundary condition. The flow field and the electric field are coupled through the Bernoulli equation, the dynamic boundary condition. And the electric fields become active, can modify the motion of the fluid only when the interface is disturbed. And in the system, gravity, surface tension, and electric force are all considered as the restoring force. I would like to say, in some sense, the electric field and the flow field are opposite. Because the voltage potential is continuous throughout the system, so the tangent derivative of the voltage potential is continuous across the interface. But these 2 fluids are of different permittivities, so the normal derivative of the voltage potential is discontinuous when the system is perturbed. However, in contrast, for the flow field, the normal velocity is continuous because of the kinematic boundary condition, but the tangential velocity is discontinuous across the interface. So they are quite different. Okay, so now this is a fully nonlinear problem, and you can linearize the system, and you can obtain the dispersion relation where f is the phase velocity. In the long wave limit, well, wave number k is close to 0, then you can write down the approximation for the linear dispersion relation. The approximation is as follows, and it is quite obvious to see that the system can be regularized. Well, the electric field can regularize the Rayleigh-Taylor instability if rho minus is smaller than rho plus, but this term is the second term is positive, can regularize the Rayleigh-Taylor instability. And the figures from left to right, the stress of the electric field increases, and you can see clearly that show clearly the stabilizing effect of the electric field. and the F squared starting from negative and become positive always. As shown, so the Rayleigh-Taylor instability is stabilized for sufficient strong electric field. However, if one of the fluid layer is of infinite depth, then the electric field can provide the dispersive regularization only to short waves. Then if one layer is infinite deep, and then we cannot regularize the long wave instability like the Rayleigh-Taylor instability, but we can still regularize the short wave instability like Kelvin-Helmholtz instability. That's the linear dispersion relation. We next try to prove the fully nonlinear problem is a Hamiltonian system. Without electric field, it was Zakharov who first proved that one layer free surface water wave problem is a Hamiltonian system. The result was extended to interfacial waves between two immiscible fluids by Khusnutdinova, Benjamin, and Tom Bridges in 1990s. For EHD waves, the Russian group knew the Hamiltonian, but I didn't find a very detailed proof. For free surface waves, the Hamiltonian is the total energy, and the canonical variables are the surface displacement and the surface velocity potential. For interfacial waves, the situation is very similar. The only difference is that one canonical variable changes. It becomes a velocity, a potential jump across the interface. It is very natural to guess that for EHD waves, the Hamiltonian is also the total energy, the sum of the kinetic energy, the potential energy due to gravity, potential energy due to surface tension, and the potential energy due to electric field. As mentioned before, only when the interface is perturbed, the electric field becomes active and contributes to the fluid motion. Thus, we can use the perturbed voltage potential as a min unknown. We can subtract the background electric field by introducing W as a new unknown. And then we can rewrite the boundary condition associated with the electric field with the new unknowns. It is obvious that these two conditions only depend on the interface displacement. This fact implies that we might have the same canonical variables as the case without electric field. Okay, so to prove this assertion, we only need to check the variation derivative of the electric potential energy. The key is how to take the variational derivative with respect to eta, since when the interface varies, the field variables W and phi also change. For example, the variation in eta results in the variation of the voltage potential W. And the quantitative relationship between these two variations at the interface can be obtained through the boundary condition, the continuity of electric displacement field. The derivation is a bit complicated, and I do not intend to go to the tedious calculations. Okay, so let's go back to the previous slides for a while. The kinetic and the kinetic and electric energies are written with field variables, W and phi, not interface variables. However, if we introduce the Dirichlet-Neumann operator, which is the most important operator in potential theory, which maps the Dirichlet boundary condition to the Neumann boundary condition on the interface by solving the Laplace equation, these energy expressions, the kinetic energy and the electric potential energy, can be rewritten using interface variables with pseudo-differential operators, or the blue ones. And we can now propose a systematic routine in the Hamiltonian framework to derive asymptotic reduced models based on the Dirichlet-Neumann operators. The routine steps are as follows. Step 1, expand the Dirichlet-Neumann operators with specific spatial scales. For example, if we assume the lower layer is shallow and the upper layer is deep in comparison with the typical wavelengths, and then we can introduce small parameters and expand the Dirichlet-Neumann operators about small parameters in respective layers. And now step 2, based on the expansion in step 1, we can expand the pseudo-differential operators associated with the kinetic energy and the electric potential energy. Step 3, we can truncating the expansion at some order, yards, and approximate Hamiltonian. And the final step, step 4, we can take the variational derivative of the approximate Hamiltonian Yaza reduced model. Based on the method that we proposed, various kinds of weakly nonlinear models, if imposing smallness assumption on wave amplitude can be derived. It is also possible to derive strongly nonlinear models without a restriction on wave amplitude. For example, we derived 2 strongly nonlinear models for one layer shallow and the other layer deep, such like very similar to the Benjamin equation, but we didn't propose smallness assumption on the wave amplitude. And since these reduced models come directly from approximate Hamiltonian, they naturally conserve energy, which can be used, for example, to check whether the numerical is okay or to check the stability properties of solitary waves. These multi-scale models derived in the Hamiltonian framework provide good approximations and the theoretical underpinnings for small and moderate amplitude solutions in various asymptotic regimes. However, it is still necessary to seek solutions in the primitive equations, the 4 Euler equations, to understand the fully nonlinear wave phenomena, such as a global bifurcation and the limiting configurations of traveling waves. As a first step towards understanding the fully nonlinear feature of electrohydrodynamic waves, we confine ourselves to the 2-dimensional problem and search for solitary waves in the 4 Euler equations, using a holograph transformation that exchanges the independent and dependent variables. We can conformally map the lower and half layers onto infinitely long stripes in the phi psi plane, where psi is a string function, which is a harmonic conjugate of the velocity potential. The conformal map helps to transform an irregular domain to a regular domain, and then we apply the Cauchy integral formula in the transformed plane to obtain boundary integral equations. Since the velocity potential is discontinuous across the interface, as I said before, it is customary to introduce an auxiliary function to connect the velocity potential right above and below the interface. Finally, the boundary integral equations and boundary conditions are discretized and solved by a Newton iteration method. What we improved in here is we constructed the Jacobian matrix exactly rather than using the numerical approximation, and this helps to push the solution branch much, much further. Now, we first compare numerical results of the reduced model against the computations of the 4 Euler equations. We consider the Rayleigh-Taylor stable regime, where the density ratio of the upper layer to the lower layer is smaller than 1. The density ratio is R. Furthermore, we assume the surface tension is very strong and the depth ratio is large. So this is the Benjamin regime, right? And in this regime, single trough depression solitary waves can be found for all values of R. And the R is taken as 0.3, 0.5, 0.7, 0.9 from left to right on the in the left figure. Well, the Benjamin equation, which was proposed by Benjamin in 1992, it's a dashed line in the left figure, generally give good predictions for small and moderate amplitude solutions. However, the strongly nonlinear models that we proposed, the dotted line, shows excellent agreement even when wave profiles almost touch the bottom. We push the solution to the limiting configuration in the computation of the 4 Euler equations. It is found that the touchdown phenomena occur while approaching the static state, regardless of the density ratio. When it tries to touch the bottom, then the speed of the translation of solitary wave becomes 0. It's a steady state for whatever R is. Okay, so next, I try to convince you that the electric field has a significant impact on the physical system being investigated and can change the qualitative nature of the interfacial solitary waves from various perspectives. First of all, due to the stabilizing effect of the horizontal electric field, the upper fluid is allowed to be heavier than the lower fluid. That means we can explore solitary waves in the Rayleigh-Taylor's unstable regime. The density ratio is allowed to be bigger than 1 when the electric field is strong enough. And this is the example with the density ratio is 1.1 and the electric field is 2.8. It's quite strong. And then we can find the traveling wave, solitary wave solutions for this set of parameters. Okay. Next, in the absence of the electric field, it is quite well known that solitary waves cannot exist if density ratio R equals 1. So if there's only the capillary, if the interfacial capillary waves, solitary wave doesn't exist in this situation. And this situation will change if one applies an external electric field. Solutions are of particular interest if we ignore the gravity and ignore the surface tension. If we only have electric field, solutions are of particular interest. That is, the horizontal electric field provides the only restoring force for the wave system. Then this is a numerical solution for this situation. And the speed amplitude bifurcation curve is on the left, is shown, which features a snake-like behavior with several tuning points, starting from the bifurcation point and following the branch. A local bulge appears in the middle, and the solution is no longer similar to the Sech-squared soliton solution. It's not like the KdV soliton. Further down the bifurcation curve, the bulge rises and expands, and ultimately becomes two fundamental depression solitons sitting side by side. This is the case for R equals 1. For R less than 1, in the Rayleigh-Taylor stable regime, the density ratio is less than 1. Interfacial gravity waves without electricity, without surface tension. This situation has been studied extensively. One of the most striking findings is the broadening of the solitary pulse. That is, the midsection of the interface develops a plateau that becomes infinitely long when the wave speed approaches a limiting value, and the ultimate become conjugate floor. We attempt to learn the modification of the electric field on the broadening phenomenon. So we found two types of solutions. Elevation wave, which is the middle point is positive, so displacement middle is a positive displacement at the center, and the depression wave with a negative displacement at the center. Both branches are found, and we will see what's going on. So this is the elevation wave. For the elevation wave, the situation is very similar to the gravity wave. And so you see the plateau expanding in the middle. However, the depression wave is very different. You see the depression wave. For the depression wave, however, the depression wave develops two plateaus during the broadening process. The connection between the two stays fixed, and either plateau expands in one direction only. So this is very different. Also, in this situation, so as the broadening phenomenon occurs, the electric field may also excite oscillations on the solitary pulse. And a typical example is shown in the movie. Trace the bifurcation curve. The KdV type solitary waves become broader and broader by adding more and more oscillations on the solitary pulse. Okay. Finally, I would like to say a few words about what we can learn from electrohydrodynamic waves in the nonlinear wave aspect. What is the conventional wisdom of nonlinear waves? Take a linear wave equation, add a little dispersion, add a little nonlinearity. What you get solitary waves. The most famous example is the celebrated KdV equation. Why do we have solitary waves? That's because the dispersion disperses, while the Berg's type nonlinearity steepens the wave. These two effects can miraculously balance each other, resulting in the formation of a Sech-squared soliton solution. KdV equations and other equations of this type was derived in a very similar situation, with slight different situation, arise when the linear waves at wave number k equals 0 are non-dispersive. This is usually called a long wave approximation. In water wave problems, the long wave approximation is relevant, for example, for Charlotte. What do I mean by non-dispersive? For a dispersive wave frequency is a function of wave number, which means waves with different wave number propagated with different speeds. Non-dispersive point means if we Taylor expand a frequency at a particular point to leading order, the leading order should be a linear function, right? Omega is AK plus B. But for non-dispersive point, K is 0. So to leading order, the wave frequency is proportional to the wave number. So the tangent line goes to the origin. So this is called non-dispersive point. But the non-dispersive point not only happens at K equals 0. So there are several water wave problems where the linear speeds are close to non-dispersive near a wave number other than 0. So the simplest example is a capillary gravity wave in deep water. The left panel is for pure gravity waves in shallow water, the KdV regime, and the solid line is the dispersion relation. The dashed line is the tangent line at the origin, which shows that K equals 0 is a non-dispersive point. So red panel is the dispersion relation for the capillary gravity wave in deep water, and the non-dispersive point occurs at K equals 1, since the tangent line at this point goes through origin. So that means the non-dispersive point can occur both at 0 wave number and non-zero wave number. What are these two cases have in common? At the non-dispersive point, omega equals ck, the phase velocity, the propagation speed of wave crest, and the root velocity, which is the derivative, right, are the same, are equal by definition, right? Because omega equals ck is just a proportion. If we calculate the group velocity in terms of the phase velocity, it is easy to see that the non-dispersive point occurs at either k equals 0. If Cg equals Cp, then either k equals 0 or Cp prime equals 0. When Cp prime equals 0, it must be a local extrema of the phase velocity. Okay? Since at the non-dispersive point, the linear speed, group velocity, and the phase velocity are equal, we can expect solitary waves bifurcating from this point. So it seems that there are only two types of solitary waves found in the waterways, the KdV type soliton and the wave packet type soliton. Solitary waves bifurcating from K equals 0 is a KdV type, and the K is not bifurcating from Cp prime equals 0, but the K is not equal to 0 is the wave packet type. Now, our question is, except these two types, is it possible to find other types of solitary waves? And in fact, introducing the electric field provides an opportunity. That's because the introduce of the electric fields makes the dispersion relation much more complicated than the classical water wave problems. And the following dispersion relation is possible. In the Rayleigh-Taylor unstable regime, for special sets of parameters, the global minima of the phase speed is attained at both k equals 0 and k is not equal to 0 simultaneously. And thus, we can expect a mixed type of solitary waves, which is a KdV and a wave packet mixed type. So typical numerical experiment shows a typical wave profile that show in these pictures. These solutions feature a wave packet sitting on the KdV puffs, and they are neither the KdV soliton nor the wave packet type. Such a peculiar wave phenomena arises due to the complicated dispersion relation resulting in the long and the short wave interactions. So bifurcation of the newly discovered, this is an ongoing project, we haven't finished this project. The bifurcation mechanism of the newly discovered solitary waves cannot be described by a single KdV or single NLS equation. It is a particular case of the long short wave interactions and the Murray's-Roth investigation. For example, we know KdV soliton decay exponentially, but the wave packet solitary like capillary gravity waves in deep water decay algebraically. So what is the decay rate of the newly discovered solitary waves? Decay algebraically or exponentially? We don't know. And what is the bifurcation mechanism? Does it bifurcate from 0 amplitude, or they can only exist with finite amplitude? Also, so these questions are very interesting, and it is also very interesting to seek KdV wave packet mixed type solutions in other nonlinear wave systems. That's what I want to talk today, and I have to stop here, and thank you very much. This is a reference for this talk, and yeah.
Okay, thank you very much. We have some questions.
Sorry, I ran out of time a little bit.
It's all right. We started late.
So I have a comment and a question. So it's mostly about first half of your talk. So first of all, with Hamiltonian formulation for two fluids, you mentioned it was kind of not done in details before. First of all, it was done in my work with Evgeny Kuznetsov, who you showed here in 1995, that we introduced Hamiltonian formalism in all details for two fluids. But when Nikolai Zubarev, what you showed here on the right, he basically for 25 years, he studied in Hamiltonian formulation all cases which you describe in great details. As basically, he was elected in Russian Academy of Science, member of Academy of Science, just for his main achievement. So I think with Hamiltonian formulation for transverse longitudinal fields, it was really done in absolutely great details the last 25 years. So do I understand that basically your contribution here to do numerics for these equations, or what?
That's right, that's right.
Is that correct?
Yeah, I know the Russian group knew the Hamiltonian, but I didn't, I just write down the details of the proof, that's right.
Yeah, because my message, it was really done very well. Okay, thank you.
Thanks.
Do we have any other questions? Okay, let's thank Zhan once again. And our last speaker today is Pierre Soret, University of Lille. He will speak about observation of solid and gases in optical fibers and deep water tank experiments.